So, we continue our discussion on small oscillation. So, at first I have to correct myself about the normal modes. So, I had these doubts between N1 and N6 for a diatomic molecule. So, we had described this system. We took coordinate x1, y1, z1 for this one and x2, y2, z2 of this one, and we wrote translation, rotation and vibration degrees of freedom. So, there will be 3 translation, 2 rotation and 1 vibration degree of freedom of this system. And for translation, the first translation we wrote N1, which was we wrote it as x1 minus x2. Actually, it should be x1 plus x2, and vibration should be N6, which is x1 minus x2. So, somehow I got confused between these two. Just to show you that these are the right coordinates, let us take origin at the center of this molecule. So, let us say this is my origin, and let us assume that it is placed symmetrically in two sides of origin. Okay, so, it is not exactly in the middle. Okay, so, let us say this here. Okay, now it looks better. So, let us assume that this has an x coordinate of minus 3 and y and z coordinate 0 0 to begin with, and this has a coordinate of 3 0 0, let us say. So, if I now translate it to a new position, now if I translate it to a new position, which is let us say towards the positive x axis. So, this is my positive x direction, this is my negative x direction. Okay. So, now if the new position is such that this one has become 4 0 0 and this becomes minus 2 0 0. So, when we were initially at this position, what was the value of my N1? The actual value of N1 was initially it was for position 1, let us say, let us call it 1, 2. Okay. So, it was N1 at 1 was 0. Now, at 2 it is minus 2, 4 minus 2, right. So, it is 2. So, it has changed. Now, let us look at this coordinate. Initially, it was N6 at position 1, it was 3 minus 3, it is 6, and N6 at position 2, it is 4 minus 2, that means 6. So, this has not changed. Now, let us assume a situation where the molecules are vibrating. So, let us call it position 3, and in vibration what happens, whether either both the molecules go out simultaneously or they come in simultaneously, right. So, let us say they have at this point of time they are expanding. So, an instantaneous position is such that let us say this is 4 0 0 and this is minus 4 0 0. So, let us see what happens to this coordinate first. N1 at position 3 is minus 4 plus 4 0, and N6 at position 3 is minus 4 minus 4 becomes 8. So, you see there is a change between these two, whereas it is a change between these two, but there is no change between here and here. So, when there is a translation motion from 1 when we come to 2, this coordinate changes. When it is a vibration motion from here to here, then this coordinate changes. Okay. And otherwise it remains unaltered. So, that means it is a proof that this one is actually a translation degree of freedom, this one represents, and this one represents a vibration degree of freedom. Interesting to note is that if you now want to express x 1 and x 2 in terms of n 1 and n 2, it is absolutely possible. So, you can write x 1 is which is equal to n 1 plus n 2 or n 6 by 2, and x 2 which is n 1 minus n 6 by 2. So, the transformation from so normal mode, as I said, at right now we are taking normal mode as a combination of Cartesian coordinates. So, similarly the Cartesian coordinates can also be represented as a combination of normal modes, right. Okay. So, this we will keep in mind, we will definitely come back to normal modes in lot more details. So, what we did so far was we kind of able to formalize the discussion on small oscillation by writing the kinetic energy and potential energy matrices in a certain form, in a particular form, and we derived the Lagrangian of the system, the equation of motion for a coupled system. But before we go into that, let us solve some quick problems, quick questions, which does not include any of this tough mathematics which we are going to deal with next. Actually, the mathematics is not very tough, some of it is already familiar to you. These are primarily eigenvalue equations that we need to solve. But better before we go there, it is better if we try our luck with some easier problems, which actually it is more conceptual in nature. There is not much mathematics involved. Okay. So, the first problem is, this is your classroom problem set for small oscillation. So, the first problem is a particle is in equilibrium under the action of two attractive forces, both properties both proportional to the distance from the force center with force constant mu and lambda respectively. The particle is slightly disturbed towards one of them, so that the period of small oscillation is given by this particular formula. Okay. So, how do we solve this? First of all, let us look at this situation. We have one particle which is in equilibrium with the action of two forces, two attractive forces from both sides. Now, an analogy of this system, we do not know what type of force is this, but we can directly draw an analogy by adding two springs in two sides of this mass m. Okay. One with spring constant mu, one with spring constant alpha, right. We can do that. I mean, right now we are not, I am just taking this an analogy, don't take this as a spring constant as of now, but we can treat it, we can treat a system in the same manner, a system like this in the same manner. Okay. So, when it is in equilibrium, a system can be in equilibrium only when the forces acting on it is in balanced state. Now, when is it balanced? It is balanced when we have, let us say the distance is x 1, the length is x 1 and the length is x 2. So, as I said, the forces are proportional to the distance, attractive forces, and the forces are attracting to both ends. So, we have mu x 1, that is f 1, and f 2 is equal to alpha x 2. For equilibrium, f 1 has to be equal to f 2, which gives you mu x 1 equal to alpha x 2. Okay. Now, let us assume that it has been displaced from its equilibrium position, which is this, let us say, by some in one direction, let us say in the positive direction, by small x, or some small displacement x. Right now, if we look at the force equation, write down the force equation, net force will be in which direction? The net force will be towards the position of equilibrium, because it is a if a system is slightly disturbed from its equilibrium and if the equilibrium is stable, then the restoring force will be towards the equilibrium. That is why it is called a restoring force to begin with, right. So, it is a stable equilibrium, and we want to find out the force. So, force F, which will come with a negative sign because it is a restoring force, will be given by mu x1 plus x minus alpha x2 minus x. So, this is the force towards this direction, that is the force towards that direction, this force wins. So, that it comes with a minus sign in the final equation. Anyway, so it is mu x1 minus alpha x2, okay, and then we have x mu plus alpha, right. And by virtue of this relation, these two terms, this combination will give you 0. So, the net restoring force, when I write the equation of motion, it will be mx double dot is equal to F, which will be equal to minus x mu plus alpha, right, clear. So, if this is the case, we can compare it with x double dot plus omega square x equal to 0, and we immediately see that omega square is mu plus alpha by m. So, omega will be this. Okay. So, this is your answer, clear. Okay. So, what we did was we just wrote the force balance equation. From there we found out the net restoring force, wrote Newton's law, this minus sign is due to restoring force, and from there we just brought it to the familiar form and frequency, done. So, this is how we solve problem number 1. For the next problem, we look into the double potential, double world potential. Potential function is given by V equal to 1/4 b x to the power 4 minus half a, sorry, it will be actually x square. Okay, I have to rectify this. The second term will be minus half a x square, where a and b are positive constants. Okay. So, we have two parts. First of all, how many turning points does this potential has? We have to say that we have to look into that and locate the minima of this function and determine the frequency of small oscillation about it. Okay. So, there are two parts to it. Anyway, let us start with this potential, which is 1/4 b x to the power 4 minus half a x square, right. Now, if you plot this function, okay, why it is called a double world potential? If you plot this function, it will look. So, see this x to the power 4 term, it will be dominating in the when x is greater than 1, but when x is less than 1, this term is lot more stronger, right. So, we have x square, or rather we have a parabolic variation for low x and x to the power 4 variation in the, I mean, this term goes down and then it will turn and go up. Okay. So, this is predominantly x to the power 4 and this is x square for the shorter values, right. So, this is more or less your x equal to 1, but anyway that is not very important. Okay. So, it will be symmetric. My drawing does not look very symmetric, but please note that it will be completely symmetric. Okay. So, I hope it looks little better. Okay. So, this is a totally symmetric case. How many turning points it has? It has 3 turning points, 1 maxima and 2 minimas. Okay. And we have to find out the position of this turning point, which is very easy. All we need to do is we need to do dV dx equal to 0. We have to set this equal to 0, and dV dx is nothing but b x cube minus a x, which will give you x b x square minus a equal to 0, right. So, we have 3 solutions. One is x equal to 0 and x equal to plus minus root over a by b. So, we know this one is x equal to 0, that we know, and this two, one is root over b by a, another one is root over minus b by a. Very good. Okay. then we have to find out the frequency of small oscillation, and needless to say that frequency of small oscillation will be valid only for these two positions. For this position there is no small oscillation. If the system is here, if you slightly deviate it, it will go into one of these minima depending on which side you give the displacement. And also we can say that because these two minimas are they are exactly identical to each other, we will have equal frequencies in these two. Okay. Now, in order to calculate this frequency, what we need to do is we need to take the second derivative, which will be 3 b x square minus a, and we have to equate it, we have to compute dv dx2 at one of this. I mean, as these two will give identical frequencies, we will just calculate at, let us say, this position. So, it will be x equal to b by a, same thing x equal to root b by a, which will be, actually it does not matter if you compute, I mean if you compute here also, it is a x squared term. So, plus b root b by a or minus root b by a, it will give you the same number. So, this will be 3 b square by a minus a, is it right? Right, 3 b square by a, which will be yeah, 3 b square minus a square by a, yeah, a by b. Oh, sorry, it is a by b, not b by a, that is why, sorry, it is a by b, I am sorry. See, this is the problem with a virtual classroom. In a real classroom, you would have got it before me long time back. We just wasted 1 minute, let us say. Okay, that makes more sense. So, it will be a by b. So, 3 a minus a, which is nothing but 2a. And if it is 2a, then and you see every potential can be brought into the, especially one dimensional potential can be brought into the form of half k x square, and in this case k is equal to 2a and frequency omega will be root over k by m. So, in this case frequency will be root over 2a by m. Okay. So, this is your final answer. Okay. So, whichever minima you choose, you will have this frequency for small oscillation. Fine. Another problem, the third one. Okay. Third one we can do also before we go into the mathematics. Third problem is the following. Lagrangian of a system is given by L equal to alpha q dot square minus beta cos q, where alpha beta greater than 0, and these are constants. What is the value of q corresponding to stable equilibrium? That is the first question, first part, and then we have to once again obtain the frequency of small oscillation about the position of stable equilibrium. So, in principle it is the very similar problem with the I mean almost similar problem to the previous one. We have a potential given. Okay, potential is not given directly, but when you write alpha q dot square minus L equal to alpha q dot square minus beta cos q, it is obvious that this one is the kinetic energy and this one is the potential energy, is not it? So, we have kinetic energy here and potential energy there, and if you now take the potential energy, which is a function of q as beta cos q. So, first of all we have to find out what is the minimal position of this, and there is a very familiar potential, right. It is a oscillatory potential, it has a value of 1, I mean let us say beta is equal to 1, let us say. Okay. So, if not, then we will have a value beta at x equal to 0, then it will oscillate for forever. It is a infinitely long potential. So, there is not one minima. Okay. Sorry, this is not a good drawing once again. It is not a good drawing either. Anyway, so there is no one minima to this system, but a series of minimas. First one comes at where? Where does it come? It comes at pi, right? And the value will be minus beta. Does not matter. Whatever is the value, as I said, the absolute value of the potential is not important. We can always set that equal to 0. What is important is where does it come. So, it comes at pi, then at 2 pi it is again a maxima, at 3 pi once again it is a minima. Okay, so, again my drawing is never very good. Okay, so, once again it will have the same amplitude and it will go on. So, we can say that the minima position of minima is general position is given by q equal to 2 how do you describe this? What you can do is we can write 1 plus n pi, right, where n is equal to 2, 4, 6. So, it will or 0 actually, it starts from 0, right. Yeah. So, we can or actually it is not needed, we can simply say n pi where n is equal to 0, 1, no, this is actually right, otherwise we cannot generalize, because we cannot put 0, 1, 3 like this. Yeah. So, this is better. Oh, sorry. So, n is equal to 0, 2, 4, 6, right. Okay. So, you put n equal to 0, you get pi, put 2, you get 3 pi, 5 pi, like this. Okay. Next, and we can immediately see that all these minimas are equivalent. It does not matter if the system is trapped here or in the next minima, it will give you equivalent value for your small oscillation, right. Now, in order to find out the frequency, we have to take d2v dq2 and this will be minus beta cos q, because first time you take the derivative it will be minus sin q and second time you take it, it will be cos q once again. So, it will come with a minus sign. So, if you evaluate, let us say this as at q equal to pi, what do you get? You get q equal to pi, at q equal to pi cos q equal to minus 1. So, you will get minus beta. So, in the for the small oscillation, sorry, not minus, there will be a minus coming all from here, it is a minus here. So, it will be a plus beta. So, for small oscillation, once again we can write it as half k x square. In this case, k is equal to right. In this case, k is equal to beta. So, your frequency omega will be root over k by m, which will be beta by m whole root. Okay. By the way, now there is no m here, but from this kinetic energy part, we see that alpha is playing the role of m. Not exactly, because we typically write half m q dot square. So, alpha is equal to m by 2. Oh, so we have to write m by 2. So, we have to write m is equal to 2 alpha, right. So, it will be beta by 2 alpha. Fine. This is my answer. So, we found out k is equivalent to beta and we have found out from here that alpha is equivalent to twice of m, right. or rather m is equivalent to twice of alpha, and we found out the frequency. Good. So, we solved 3 problems which were pretty basic in a sense. We do not need any, we have only found out the position and frequencies of small oscillation without discussing much about the nature of oscillation in general, and all 3 they are essentially one dimensional systems. So, system of one parameter. So, these are very simple problem which is important for concept build up, but now we have to make things more general. Okay. So, let us try that. Let us go into the theoretical discussion of small oscillation. Now, once we do that, just give me a second. Right. So, what we did already, we wrote the Lagrangian L, which is T minus V, as a I j q j a I j q I dot q j dot minus b I j q I q j. Okay. So, where I j's are dummy indices and there is a summation convention on this. From here we have found out the equation of motion, which was a I j q j double dot plus b I j q j equal to 0. And it is extremely deceptive look, because it seems like we have separated out the variables and we wrote an equation for the parameter, I mean particular coordinate q j, but this is very wrong, because there is a summation convention involved. So, the j is the repetitive index. So, actually this equation looks something like a, let us take I equal to 2. Okay. So, it will be like 2 1 q 1 plus b 2 1 sorry q 1 double dot q 1 plus b or sorry a 2 2 q 2 double dot plus b 2 2 q 2 plus a 2 3 q 3 double dot plus b 2 3 q 3, and it will go on like this, as many indices as you can think of. I have just wrote one for I equal to 2. Similarly, for I equal to 1 there will be one equation, I equal to 3 there will be another similar equation, so on and so forth. And these are all simultaneous differential equations in the in the generalized coordinates q 1, q 2, q 3 up to q n. Now, and on the right hand side of each of this equation we have a 0. Now, these equations will have solution. Oh, sorry, this equation will not have any solution. These are okay, sorry. But if we take a trial solution of the form, right, if I take q k is equal to a k e to the power I p t. If this is my trial solution, what we can do is we can write compute q k double dot, which will be equal to, so I p will come once and twice. So, it will be minus p square a k e to the power I p t, right. Now, if I substitute that for q double dot, so what we will have is, for the first term for example, we will have minus p square, okay, and it will be a 1 and it will be simply a 1. Similarly, it will be a minus sign here, minus a 2 2 p square, 2 2 p square a 2, and this will be b 2 2 a 2 Similarly, this one will be minus a 2 3 p square a 3, and there will be other terms like this. So, this is again, this equation is for I equal to 2. For I equal to 1, there will be one such equation, I equal to 3 one such equation. So, it is a equation in which it is a simultaneous equation in A and P, right. Now, please recall that, please understand that A's are, for one row of this or one particular equation, we can take A 1 common. So, we can take A 1 out, sorry, this will be A 1, okay, my mistake. This will be A 1, right. Sorry, it is not the case. So, it will be A 1, sorry, we cannot take common, right, A 2 like this. Okay. But if I go back here, if I write the generalized form once again, it will be minus p square a I j a j plus b I j a j equal to 0, right. And this, okay, when I open this, this will give you this type of equations, simultaneous equations. Now, this type of simultaneous equations, we can, so we have the indices I and j running over from, or I and j running from 1 to n. So, we have n such equations, and each of this we can group into n such quantities of A and B. Okay. And what we can do is, we can write this in form of a matrix equation, which has the following form, B A equal to p square A, where we are not writing it in component form, where B is a matrix which we found from the potential energy or kinetic energy, sorry, potential energy. A is the matrix we found from the kinetic energy, and A is the matrix of the amplitudes, the column vector, right. So, this is it's just another representation of the same equation here. It is in the component form, which will look something like this, and this is in a proper matrix form. Now, is not it something similar to the eigenvalue problem we have solved? We have solved eigenvalue problems, which has the form, let us say A x is equal to lambda x. Now, and if you recall, what we did was, we took A minus I lambda into one side and x, and we put it equal to 0. So, similarly, we can do the same thing here, A minus p, B minus p square A times A, where A, this capital A is the amplitude column vector, okay, column vector represented by representing all the amplitudes for all the mass points. So, this equation, this is a set of simultaneous equations. So, like one we have written here. So, there will be n such equations, coupled equations, and they will have solution if and only if the determinant of this term vanishes. So, the condition to have a solution is the determinant matrix or determinant of this matrix equation vanishes. So, the condition will be determinant of minus p square A I j plus B I j will be equal to 0, right. So, this is the condition. Now, if this condition has to be satisfied, what we will get? Let us say we find out equations, we open this determinant, and it will be a polynomial of degree n in, or rather degree 2n in p or degree n in p square. So, solving this, we will get p 1, p 2 up to p n, right. So, this will be the solution, or rather p 1 square, p 2 square up to p n square. Now, this will give us distinct values of the eigenfrequencies. Okay. So, these are all frequencies. So, these we can call the normal frequencies, of oscillation, right. Now, from here we cannot really conclude much, because these are the normal frequencies and we just say okay, right now we know nothing about them. Now, in order to gain more insight into what are the properties of P and what are the importantly what are the properties of A, these are actually the amplitude matrices. So, we can call them the normalized amplitudes, right. So, what are these properties? In order to do that, we have to go little more into the mathematics. Now, right now we am not sure if we can go into the details, but one thing I can tell you before we start that, maybe in the next lecture I can tell you something. Let us assume that, so what is the system we have taken? We have taken a system of n coupled oscillators. Now, each of this in a general motion, each of this will have some degree of vibration, or it could be, I mean, it will have some amplitude. Now, that amplitude could be 0 for some cases for certain mass points, but in general there will be an amplitude. Now, this amplitude will also have, so each of this amplitude matrix will also have n number of components, because understand the situation. Each of these eigenvalues, these are actually the eigenvalues of this eigenvalue problem, right. Each of these eigenvalues will correspond to one eigenvector. One eigenvector is one column matrix of n. So, we have for each of this it will look something like this. We have 1, 2, 3, 4 up to n quantities. Okay. That is for each of these frequencies. Now, for n such frequencies, we have n such matrices, n such column matrices, which will have n number of entries each. So, at the end A, the overall description of A actually is spanned into an n cross n dimension. Think of it, just take a 3 by 3 system. Let us say we have 3 mass points coupled. Each mass point oscillates, or let us say, so that means the system in general will have 3 normal frequencies. Now, for each normal frequency, each mass point have one certain type of amplitude. So, we have 3 quantities. So, for second normal frequency, we again have 3 independent quantities, right, defining the amplitude of each of these mass points. So, for 3 total normal frequencies, we need to have 3 into 3, that is 9 number of amplitude values in order to get the full description, right. So, that is why I have written it's the dimension of total number of amplitude elements will be n into n, right. So, the general solution q k needs 2 indices. It can be written as a k l e to the power I p l t, where there is a summation over L. So, we will take this generalized form. Okay. When we will take an example, you will understand more in more details why these 2 indices are required. I think you already have a feel, because as I said, if I have a system of 3 coupled oscillators for each and 3 frequencies, for each frequency we have 3 amplitudes. So, for 3 frequencies we have to altogether 9 amplitudes, right. So, we will take examples and see. Right now, we are writing this in this particular form. Okay. Try to understand that q k represents the amplitude of, or the total overall displacement of any particular mass point k, which is a function of both L, I mean k, that index, and there is another index on which the summation runs, and that index actually represents the variation in normal frequencies. Anyway, so we will start from this particular generalized form of solution and develop from here and see. Okay, thank you.